Hi everybody, and welcome back to Philosophy of Cognitive Science with me, Dr. Josh Redstone. Today's lecture is Connectionism Part 1. So today we're going to be taking a look at a radically different computational paradigm, radically different from the physical symbol system approach, which is what we've been looking at up until now. Before we get into that though, I just want to mention to you that I will be riffing quite a bit for this lecture. I've drawn on materials that, come from outside of this chapter in Clarke's book. Clarke covers this material very well, but I feel like some few details are kind of missing from this chapter, at least by comparison to how I usually teach about connectionism and neural networks in Cognitive Science 2001 when I teach that course. So I'm going to try and fill in what I see as a few lacunae here in Clarke's chapter with other stuff, and I'm going to be mentioning things on the fly that I come up with just off the top of my head. So if you don't usually take lecture notes, do make sure that you do so this time. And if you already do take notes, well, just keep taking notes. So last time we finished up our discussion of patterns, contents, and causes, which has to do with some concerns we can raise about the physical symbol system approach. My recap, by the way, won't be too substantial today, but we talked about different kinds of causes last time. You know, we talked about typical like billiard ball type causation versus scattered causes and ungrounded causes. We talked about stances, so we talked about the intentional stance a little bit more, and of course we also talked about upgrading the base believer. All of this has a lot to do with Dennett's intentional stance, which we talked about last time, as I mentioned, but which I talked about even more during the first part of our lecture on patterns, contents, and causes. So do go ahead and review those if you feel like you need to, if you feel like you're not clear on any of that material yet. Or, of course, feel free to send me an email or a message on Discord. Anyway, now that we're done with our brief recap, and now that you're all ready to take some notes, we're going to start looking at what connectionism is. What is this radically different paradigm that is sometimes called connectionism, or parallel distributed processing, or artificial neural networks? You know, what is this radically different style of computation? Let's find out. All right, so Clarke begins this chapter by drawing your attention to the fact that there are two different variations of computationalism. One is, of course, symbol systems, the physical symbol system hypothesis, and the systems that hypothesis describes, and the four characteristics we looked at that characterize physical symbol systems. All of that is one variety of computationalism. It's what we've been talking about pretty much mostly up until now. It's inspired to a great deal by early AI research, so we're talking Turing, Shannon, Newell, Simon, those figures. Of course, there are linguistic influences in there as well, for example, from Noam Chomsky. Of course, the earlier developments in logic that we looked at in our Meat Machines lectures are an important part of this. But all of this is, all of this characterizes minds or cognition as these systems that are basically these syntactic engines, right? They operate on syntactic properties, but they respect semantic content. So, another important thing, of course, which we've kind of talked about here and there, is that these systems are semantically transparent. If you look at the code, for example, you can work out what means what. Even if the representations are not coded in a very semantically transparent way, ostensibly anyway. For example, if you have a chess playing program that encodes information about the pieces by representing each piece as like K or R or P, you know, for king, rook, pawn, so on and so forth. Even if it's not that clear, even if you use arbitrary squiggles to represent those items in the cognitive economy of such a system, you could still work out what everything meant. right? By observing the system, seeing what it does, looking at how it behaves. You could see by looking at it what it does and what the symbols represent. So that's going to be very important because, as you'll see, connectionist networks don't have this property. So that's the first variety, which I won't say too much more about because that is what we've been talking about pretty much exclusively up until now in this class. But the other variety is, of course, the connectionist variety of computationalism. As I mentioned earlier, this is sometimes called artificial neural networks or parallel distributed processing for reasons that will become clear in this lecture. Now, unlike the symbolic paradigm, which is inspired by early research in logic, linguistics, computer science, and so forth, this is biologically inspired. Connectionism is biologically inspired, but in a fairly loose sense. It's meant to be, connectionist networks are meant to be roughly analogous to the way that neural networks in the brain compute information, but of course there are still vast differences between brains and artificial neural networks. But the point is they are biologically inspired. We can question the extent to which any given network is actually biologically plausible, though. Some are more biologically plausible than others. And these networks are made of simple processors called units or artificial neurons. And these are all connected to other units. Usually they're arranged in layers, which we're going to take a look at in a moment. But they're connected to all these other units, and each unit is sensitive to local influences. So just whatever the units it's connected to are doing is what it is sensitive to. But because those units are connected to other units, we get this kind of interesting distributed sort of representations that happen in neural networks. As we'll see today, representations in artificial neural networks are not neat, discrete symbols like we find in the physical symbol paradigm. They're not nice collections of zeros and ones or symbols on the tape of a Turing machine or squiggles on a page in a Chinese room. It's very different from a symbolic approach. Rather, as I mentioned a moment ago, we call them distributed or sometimes sub-symbolic representations because they're not neat little items. They are rather distributed across the entire activation space of a neural network. And we're going to take a look at how this works a little bit later on in today's lecture. So what are some of the interesting characteristics or properties of an artificial neural network? Well, I will place an image of an artificial neural network up here. Typically, these networks, as I mentioned, are composed of units that are connected in a series of layers. So if you take a look at the figure that I've placed here, you will see we've got 4 layers. We have an input layer, and the units in the input layer encode the information coming into the network, and we'll talk about the format of that information in a moment. And the units in that layer are connected to the units in the hidden layers. And the units in the hidden layers are in turn connected to the output units and the output layers. Now, it's important to notice, again, in this diagram here, that in each layer, none of the units in the input layer, for example, are connected to any of the other units in the input layer. But every unit in the input layer is connected to every unit in the first hidden layer. Likewise with the first hidden layer to the second hidden layer, and the second hidden layer to the output layer. So for this reason, we say that these neural networks are parallel processors, like brains are. They're not like Turing machines where we do one thing at a time. Many computations are happening in parallel, and then all of that activity is feeding forward through the network while it's doing so. So that is why we call this approach parallel distributed processing, because neural networks are massively parallel in this way, rather like how our brains are meant to be parallel processors. And this is one of the ways in which these are biologically inspired, of course. So we can think of each unit as a neuron, an artificial neuron. Sometimes these are called perceptrons. And networks like this one, which is a multi-layered perceptron network, is basically a whole bunch of perceptrons connected together in a certain way in a certain number of layers. The connections, of course, are like synapses in the brain. So in the brain, we have neurons which have axons and dendrites. These are two kinds of extensions from the cell that will kind of almost but not quite touch. And there is the synapse where they meet, and information travels across the synapses. So the connections between the artificial neurons are like synapses in the brain. Now, as I mentioned, a lot of artificial neural networks are constructed out of perceptrons. I'll put a perceptron right here. Basically, we can see here the different inputs going into the unit. They're all indicated with the number I, with certain subscript numbers. So I1, I2, I3, IN, that's the number of inputs. The little circles that say W subscript 1, subscript 2, those indicate the weights of our connections. So basically any signal traveling through this connection is multiplied by a weight. Then when it gets to the inside of the unit, you'll see why I'm using air quotes in a moment. All of these weights are summed, and we see if the sum of activity going into the unit it meets a certain threshold of activity. That's what this little x equals sum of wj, ij, all of the math in there that looks really intimidating, basically just says take all of the inputs, multiply them by their respective weights, sum all of that up, and see if it exceeds the activation threshold, which is represented by t. So if x, our sum of all the weighted connections, is greater than t, our neuron will output a signal to the next neurons in the next layer. So this is how basically information travels through a neural network. I've been using air quotes here, saying going into the units, and these are artificial neurons. This picture of a perceptron and the earlier picture of a multilayer perceptron network are just that. They are just pictures. Really, these are mathematical functions. We don't look at neural networks and look at this node and look at that node in the network and this unit and this connection. It's not really how it works. These are graphical representations to make this easier for us to understand. Really, what neural networks are mathematical objects. They're like mathematical systems, and they compute lots of different functions, like these activation functions in this single layered perceptron right here. Now, also, I should point out that nowadays there are many kinds of artificial neurons, and they have all kinds of different activation functions. We have linear functions, where the greater the input, the output increases linearly in proportion to the input. We have sigmoidal functions that kind of, if we look at the inputs and outputs, they form a kind of S shape on a graph. We have step functions. Lots of different kinds of mathematical functions that we can use for our artificial neurons. But those details need not detain us here. What I want you to know is just that these pictures that I've been showing are just pictures, meant to make it easier to understand what is going on in the units and between the connections in between these units in artificial neural networks. So just to kind of recap what I just said, we have these artificial neurons and they receive inputs. We can represent the number of inputs with n. There are n inputs. Could be a few dozen, a few hundred, doesn't matter. So we assign a numerical value to the weight, which we represent with W of each input, which, as we saw, we represent with I. And usually this is about a value between 1 and -1. Why a value between 1 and -1? Why not 1 and 0? Well, in the brain, some synapses are excitatory. They spread more activation through the network. Some synapses are inhibitory. They inhibit activation through the network. So by allowing our weights to be multiplied, by numbers between 1 and -1, we can have excitatory synapses or inhibitory synapses in our neural network. So as I mentioned, we can use this to calculate the total input into a neuron. So we multiply each input going in by its weight, and this gives us an activation level for each of those connections or each of those synapses. We sum all of that, gives us a total that we call x, and we want to see if the value of x is greater than our activation threshold. T. If it is, the neuron fires and outputs a signal, and all of these inputs and outputs are, in an artificial neural network anyway, ordered series of numbers called vectors. So you hear a lot of talk about vectors and vector spaces with artificial neural networks. It all sounds very complicated, but really it's quite simple. Really, a vector is just an ordered series of numbers. So if you want to sound smart in front of your friends, you can talk to them about vectors and neural networks, and don't let them know, but it's actually not really as difficult as it sounds. Let's say, for example, that I wanted to have my neural network be able to look at a picture, okay? And let's say my picture, let's keep it very simple. Let's say my picture is a square and it is 10 pixels by 10 pixels. Okay. And let's say also that my picture is black and white. So it's like grayscale, right? My pixels can be on or off. On they're black and off they're white, and maybe my picture is of a simple happy face or something, right? How is my neural network going to look at that? Well, we have 10 pixels by 10 pixels. What is 10 by 10? 100. So I have 100 pixels in my image. I want my neural network to be able to take a look at that, so I need to transform my 10 by 10 pixel image into a 100 number vector. And each number in that vector could represent, say, whether the pixel in an image is on or off. So I can turn my 10 by 10 image into a 100 number vector of zeros and ones. And that is how the neural network would be able to see the picture. I would have to have 100 input units in this case, one for each pixel in the picture. But that's what would happen. My input vector would go into my input units, one number in the vector for each unit, or one dimension in the vector for each unit, I guess is the technical way of putting it. And then that information will feed forward through the network. And perhaps I can teach my network how to recognize a happy face versus a sad face by showing it lots of different pictures like this. That's how these vectors work in simple terms, okay? So for now, I'm not going to go into too much more detail on that, but as with many topics, I'm sure we're going to get into this again later on in the course. So for now, you have the basics. Anyway, let's move on to another example of a neural network, which is the NetTalk network, developed by Sinowski and Rosenberg, which Clark talks about in this chapter. So the NetTalk network was developed in the mid to late 1980s by Sinowski and Rosenberg. And, well, actually a lot of interesting work on neural networks was taking place in the 1980s for reasons that I'll get to a little bit later. But basically the NetTalk network took written input and coded it as speech. In other words, it did something that is known as grapheme-phoneme conversion, taking letters on a page and converting them to spoken sound, as if I were reading something out loud to you right now. Now, it used a learning algorithm to do this. It wasn't programmed to do this. There was an earlier predecessor called DECtalk, but it was programmed to do this, given explicit instructions by the programmers how to take this grapheme and turn it into this phoneme. NetTalk didn't do that. NetTalk learned how to do it. So, it had 3 layers of artificial neurons. It had an input layer, which encoded information for processing. It had a hidden layer, which partially recoded the inputs from the input layer. And it had an output layer, which determined the system's response to the input. So determined what phonetic information it would output based upon what graphic information served as its input. All of that output from the final layer, from the output layer, would be sent to a speech synthesizer to generate sound. Now, the interesting thing, again, because it employed a learning algorithm, is that it demonstrated an interesting learning trajectory. At first, NetTalk would slowly babble. It would get the incorrect phonemes from, the whatever graphemes it received. If it received a PH, it should produce a sound, right? If it receives a TH, it should make a sound, right? You see what I mean? But at first it didn't do that. At first it just kind of blah, 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 made random noise, like a baby would when a baby is learning to talk. As it iterated through more data and more training phases and updated all of its weights and connections as it did so, and I'll tell you a little bit about how a learning algorithm works in a moment, it learned and gradually became able to produce something akin to understandable speech rather than babbling. And this is one of the really cool things about neural networks, is that they hold a lot of interesting illustrative applications for machine learning, which we'll talk about from time to time throughout this class. Now, if you'd like to see more details on how NetTalk worked, you should check out box 4.1 in chapter 4 of Clark's book, Mindware. So NetTalk and other networks like this are not programmed like symbolic systems. They are trained like you train your dog. Why do we do this? It's not just because it's interesting and cool. And by the way, machine learning is not just a thing that we do with neural networks. There are symbolic systems that have learning algorithms too, like the ID3 algorithm is a very famous symbolic learning algorithm. But we're focusing on neural networks today. And the reason why we train them rather than program them is that it's just easier. Take NetTalk, for example, okay? Each connection in NetTalk, each connection between one node in a network and all of the other nodes in the next layer of the network that first node is connected to, the first artificial neuron is connected to, represents a mathematical function, right? So we've got all these units computing functions and they're all connected to one another. And there's so many connections in a neural network. I'll give you an example. In NetTalk, we had 7 groups of input units, and each of the 7 groups had 29 units in each group. So this is for individual phonemes and pairs of letters that make other phonemes. So you could have a group of vowels and a group of consonants, a group of funny sounds like and g and sounds like that, right? You know, all the different sounds. So we have 7 groups of 29 input units. And then we have a hidden layer of 80 units and an output layer of 26 units for encoding phonemes. If you do all the math, you find that there are 18,829 weighted connections in the NetTalk network. And that's just a heck of a lot of connections to manually program. And also, you don't necessarily know how to program them to get the network to do what you want. That's another reason why we train these networks rather than program them. So we train these networks with these learning algorithms. What we do when we start training a network is we have some training data, and we'll expose the network to this data in a series of what we call epochs, and it'll iterate through the training set in each epoch, and then we'll save some data later, which we'll call testing data, and we see how the network does on this new data that it hasn't seen before, that it hasn't been trained on. But before we start training the network, all of the thresholds, weighted connections are all randomly set. So the network starts as this random computer spaghetti mishmash, and then we apply a learning algorithm as we're exposing it to the training data. The learning algorithm, what that does is it tries to get the network to reduce error. So this is called supervised learning. We don't necessarily know how to program the network to do what we want it to do, but we do know what we want the network to do. We are giving the network a task where we know the right answer. Say I wanted it to be able to tell the difference between, 10 by 10 pixel happy and sad faces, or categorize basic emotions represented on such faces, right? We know the right answers. We know when the network has identified a happy face versus a sad face versus an angry face versus a surprised face, okay? So we know the answer. We know what it's supposed to be doing. And the network does its thing and probably gets a lot of it wrong. So we have our desired output and we have our actual output. And what we want to do with our learning algorithm is decrease the difference between our desired output and our actual output. Hopefully so that that error gets close to, or better yet, all the way to 0. So learning algorithms are all about reducing error, making the difference between what we want the network to do and what the network actually does as small as possible in terms of the number of mistakes that the network makes. And there are lots of different ways that we can do this. For example, on box 4.2 on page 72 in Mindware, you can read about gradient descent learning, where if you think of getting closer to an error of 0 as going down a hill, that's kind of what we're doing down here. We're trying to take a step of a certain size down a hill of error until we reduce error as much as you can. And if we get to a spot where we can't reduce any further, we have to go back up and go back down a different gradient, right? So it's a bit like trying to find the lowest point in a hilly terrain, if you like. And that lowest point will be where the network makes the least amount of errors. You know, sometimes gradient descent learning is also called hill climbing. So it's not just an analogy. We can actually invert it and do a procedure called hill climbing. But anyway, what these little gradient descents are like descents that might reduce the error of particular weighted connections in your network. So your learning algorithm is going down all these little hills and valleys, trying to adjust the weights of the network such that error is as low as it can be throughout the network. Okay, so that's one example. But the classic example for a learning algorithm with neural networks is the backpropagation of error algorithm. So let's talk about backpropagation of error now. So the backpropagation algorithm created by Paul Verbos is pretty important in the history of neural networks and cognitive science for reasons that I don't want to get into too deeply, but suffice to say, all of this research on neural networks really got going in the 1980s, but we had multi-layer networks before the 1980s. The problem is we didn't really know how to train them very well, and the other networks that we had, the single-layer networks made out of perceptrons, were limited in terms of the kinds of functions that they could compute. Single-layer networks can only compute functions that are linearly separable. I'll link you to a video that explains what that means. But essentially it means that we can only compute certain functions using single-layer networks. So we need multi-layer networks, and we can build multi-layer networks to easily compute non-linearly separable functions. The problem is, to build really big networks to get them to do really complicated things, we don't know how to train them. At least we didn't at this time. That is until Paul Verbos came along with his backpropagation learning algorithm. So remember, as I said a moment ago, when we train a neural network, what we're trying to do is give it some data, look at what the network does, and then try to reduce error. And error is the difference between the actual output of the network and the desired output of a network. Or, if you like, the actual versus desired output of any one unit in the network. That'll become important here for the backpropagation algorithm. So when we do this, again, this is an example of supervised learning. The people who created the network are training it with training data that they've chosen and an algorithm that they have constructed for that purpose. So what happens with the backpropagation algorithm is that the errors the network makes are propagated backwards through the network to update the weighted connections between all of the different units in the network. So that's essentially how it works. And again, to go back to what I said a moment ago about single layer networks, we know what inputs and outputs we ought to have. We know what the network ought to be doing given our input vector and what we expect the network to do and how we train it. So it's easy to calculate this degree of error when our network does something wrong, the entire network. But when it comes to multi-layer networks, before the backpropagation algorithm came along, we don't know, based on the degree of error between the whole output of the network and the desired output of the entire output layer of the network, We don't know based on this the degree of error that each of the units in the hidden layers is responsible for. So we don't know how to adjust the weights of those hidden units without some kind of backpropagation algorithm. That's what the backpropagation algorithm does. The idea here is that each of the hidden units does bear some degree of responsibility for the overall error of the network's outputs. So the backpropagation algorithm, without getting into the mathematical details, gives us a way to assign this degree of error to these hidden units. And once we can do that, we can modify the weights of the connections between the hidden units and the output units, and we can use this method to decrease the error that the network makes through each training epoch. So we can also apply this method to as many hidden layers as there are in the network. Some networks, like for example deep learning networks, have many hidden layers, sometimes dozens of hidden layers, each comprising many artificial neurons. So we can use variations of the backpropagation algorithm to train these networks, where we can only see the error from the output layer, and we don't necessarily know, or at least we didn't prior to the development of Verbos's algorithm, we didn't know how to assign this responsibility, degree of responsibility of error to these hidden units. The backpropagation of error algorithm allows us to do that. So it allows us to train multi-layer networks, which is pretty cool. Now, just keep in mind also that when we're talking about the way information travels through a network, activation, that is the information moving from the inputs to the hidden layers to the output layers, always moves in that direction, always forward. It's forward, always feed forward, unless it's a recurrent neural network, which we'll get to in a moment. But the backpropagation of error propagates the error backward through the network. So in most standard feed-forward neural networks, the activation is propagated forward and the error is propagated backward. Okay? So that's a little bit about the backpropagation of error and how we train neural networks. Again, this is discussed here, but not in as much detail as I've talked about here in my lecture. It's discussed in the book in not as much detail as in my lecture, I mean to say. But I also have barely scratched the surface here. So if any of you are curious or you want some more details about neural networks, talk to me. I have got lots of information for you. And I can even share some handy tools that you can use to start tinkering around with neural networks on your computers at home. It's actually pretty fun. You should give it a try. Anyway, why don't we move on to talk about some of the interesting properties that neural networks have. So as for the interesting properties of neural networks, as I already mentioned, they employ distributed representation. So where symbol systems have discrete representations, physical patterns that represent information, the patterns in a neural network are distributed across the entire activation space of the network. That is, these distributed representations are represented by the simultaneous activity of many different units in the network. Neural networks also use what are sometimes called superpositional coding schemes. What this means is that because they encode information in a distributed manner in this vector space or activation space, the way that information is represented is I guess there is no better term than to say superpositional. Perhaps it would be easier to explain this if I gave you an example. For example, one pattern of representation or pattern of activity in a neural network might represent a cat, for example, the image of a cat. And slight variations in this activation pattern might represent information about the cat's orientation in one picture versus another. Say whether it is looking at the camera or looking out the window at a bird or asking if Iken has cheeseburger. Now, this pattern might share similar patterns of activity with other similar representations of other kinds of cats, maybe maybe the pattern of activation for a house cat shares patterns of activation with with patterns of activation that represent images of tigers or panthers or things like that. And furthermore, maybe these patterns of activity for cats that share features would not share features with other patterns of activity that represent other kinds of things like wolves or dogs or foxes. So to say that it's superpositional, that this kind of representational or coding, to say this kind of coding scheme is superpositional is to say that we can encode a lot more information in a smaller space, because a lot of the different kinds of information is represented just by subtle changes in this activation pattern. So the activation pattern for a black cat and a black panther will probably share a lot. For a black cat and a white dog, probably not very much at all, depending on how the network is coded. And notice that we can represent more information this way than we can with public language words that are a lot more symbolic, like cat and panther. These are two completely different symbols, discrete symbols, the word cat and the word panther. But in a neural network, the representations of these two things, a cat and a panther, would probably share quite a lot of features. That's what it means to say that they use superpositional coding schemes. Also, they have this interesting property of graceful degradation. So neural networks are distributed, of course, and just like human brains, they can still function if part of the network is damaged. Just like if a human being has a stroke, they don't turn into a vegetable all of a sudden, at least not typically. Typically, there is still quite a lot of intact cognitive function. You will perhaps lose some abilities or suffer some disability in a particular domain, but the rest of your brain will still work fine. That's graceful degradation. And indeed, thanks to neuroplasticity, sometimes we can even recover functions when our brains have damaged. And interestingly, when it comes to neural networks, we can actually selectively damage parts of a neural network to see how the neural network actually works, which I'll talk about in a moment. But graceful degradation is something that human brains exhibit. If you have a stroke, or if you suffer from dementia, or you have a brain injury, some kind of lesion or tumor that needs to be removed, some cognitive functions will be impacted, but it will not be global. That's graceful degradation. It's not as if I mess up just a small amount of neurons, your entire brain stops working. Same with a neural network. Now, all of these properties mean that there are some interesting implications that we have to consider here. So unlike physical symbol systems, as I mentioned earlier, neural networks are not semantically transparent. We can look inside a chess computer program, or like Shank's restaurant script, or any other computer program, any other symbolic computer program, and we can see what it does. We can literally read it out of the code, or just see how it works and figure it out that way. We can see what the representations mean. We cannot do this with a neural network. They are not semantically transparent. Indeed, I could take two identical neural networks, but as soon as I start training them, I've initialized them, and they all have different random weighted connections and thresholds. And as I train them, they might achieve the same proficiency in the same task, identifying cats versus dogs, or happy faces versus sad faces, doesn't matter. Whatever I train them to do, they might reach equal proficiency, but those networks, if you were to look inside of them at all of the different weighted connections and thresholds and patterns of activation, they would look completely different from one another. So they're not semantically transparent in the way that symbol systems are. But that raises an interesting question. Is there a way that we can make sense of what these neural networks are actually doing, of how they're encoding their knowledge if they're not semantically transparent? Yes, it turns out that there are. We can use post-training analysis, for example. This is where we use statistical techniques, or, as I mentioned a moment ago, systematic interference on the network, like lesion studies for an artificial neural network, to understand how the network classifies things into sets based on the properties of those things, whether they be cats and dogs, or handwritten digits, or graphemes into phonemes, or different kinds of facial expressions. Doesn't matter. We can use post-training analysis to try and make sense of our network's behavior because it's not semantically transparent. So systematic interference could be like applied to give an artificial lesion to our artificial neural network, an artificial lobotomy, if you will, and we'll see how the performance of the network is impacted, and based on that we can work out what those neurons that we removed were doing, okay, based on the difference in performance between the network. We can use different statistical techniques too, like in box 4.3, you can read about how cluster analysis, which is a statistical technique, was used to gain insight into how NetTalk, the earlier mentioned neural network, classified graphemes and phonemes. So these graphemes represent these sounds, and it goes from basic ones all the way up to larger groups of sounds. I won't go into the details here, but you can take a look in box 4.3 if you're curious. So what I've been talking about up until now really concerns the first generation of artificial neural networks. Now, the first generation of artificial neural networks didn't really deal with time or order. Information is propagated through the network in a series of time steps, but these networks don't really deal with a dynamic environment or with events that are extended in time. This is what we tried to do with the second generation of neural networks. We saw some improvements in these artificial neural networks with respect to dealing with events that were extended in time. And some of the networks did this by incorporating a recurrent feature, a recurrent layer, which would work as a kind of short-term memory for these neural networks. And these are called, as you may have guessed, recurrent neural networks. So, as I mentioned, these have an extra layer, and it works a bit like a feedback loop. Basically, the recurrent layer remembers activation patterns from the previous time steps. And that layer stays active so that when the next vector is passed forward through the network, when it's propagated through the network, this previous activity of the network, which is kept active in this short-term memory, has an effect on how the output is generated the next time around. So the outputs of recurrent networks, unlike the first generation networks we looked at up until now, depends both on the input activity and on the activity from previous outputs, not just on the inputs, as with first generation neural networks. For example, in a 1991 publication, Ellman describes a recurrent neural network that would classify lexical items like nouns and verbs. It would take words and classify them into these groups of different lexical items. So it would be exposed to strings like this string, the boy who broke the window. That's a string of words made out of letters. And it had to predict, or learn to predict, the right words in sequences like this. So it would have to learn that the string, the boy who, can be completed by broke, which is a verb, but not by cat, dog, car, or bus, or airplane, which are nouns. So in this way, the network learned to classify lexical items into nouns and verbs, and its recurrent layer helped it do this. So basically it would get example sentences and be given new data, like say we give it a new string, like the girl who instead of the boy who. And it learns that when you have a string that says something like the girl who or the boy who, it can't be completed by having the next lexical item be a noun. The next one has to be a verb. So it has to be the boy who broke, or the girl who took, or something like that. So in this way, it learns to classify these lexical items. But Ellman's network did not just classify lexical items. It was also able to discover other categories, categories like animate and inanimate object, breakable objects, food, so on and so forth. So it wasn't able to just classify lexical items based upon whether they were nouns or verbs. It eventually learned what words referred to animate versus inanimate objects, and so on and so forth. So it used these new categories that it was able to learn to help in turn determine what each kind of word the lexical items were. Ellman, by the way, used a statistical technique called principal components analysis to understand the behavior of this network. I'm not going to get into very much detail here. I had to do a little principal components analysis for my PhD thesis, so I guess if you're feeling really ambitious, you could read that. But I'm not going to make you do that. Instead, you could check out Clark, page 78, where he talks about this. Or you could check out Clark 1993, pages 60 to 67. Or better yet, I'm going to share a video on principal components analysis down here from Andy Field, who wrote the book on statistics for this kind of stuff. Easy to understand, very funny, very entertaining to read, very informative, and he's got a great YouTube channel too, so I'm going to share that down here, and you can check out Principal Components Analysis if you're curious. Now, Clark thinks that the more temporal dynamics matter for neural networks, the farther and farther away we're moving from anything that resembles the physical symbol system hypothesis. Right? Physical symbol systems, after all, feature static or stable representations manipulated by a central processor. And as we've seen, simple recurrent networks, or even simpler neural networks, which are not recurrent, just basic feed-forward networks, don't work this way. They don't have these same kinds of neat, static, discrete representations. They have distributed representations and superpositional coding schemes, as we've seen. So for this reason, a network like Ellman's is said to employ dynamic representations. Why dynamic? Well, because the activation of the units isn't fixed. They don't function as fixed representations, as representations do in physical symbol systems, where our representations are symbol structures made of physical patterns. Rather, in Ellman's network, to quote him from his 1991 publication, every occurrence of a lexical item has a separate internal representation, even if we're possibly talking about two different instances of the same word. They will have a different representation that is sensitive to the inputs as well as what the network was doing last time. So it's sensitive to what the network output the last time, as well as where the word features into what string the network is using, that the network is taking as input. So dog might be represented by a different kind of dynamic representation in this network based on whether it features in a sentence like the dog who broke, or whether it's in a sentence like the boy and his dog. And of course, it will also be a different representation depending on what the network did last time. And that's why we call these dynamic representations. Everything is happening in real time, and it's affected by everything that has happened the last time, as well as what is happening in the system at the present time. So those are dynamic representations. Thus, Ellman, and here arguably also Clark, think we need to get beyond the idea that, beyond the idea of representations as static symbols that are stored and retrieved and manipulated like they are in classical symbolic architectures. Instead, artificial neural networks have, to quote Clark on page 79, a kind of fluid internal economy. So representations are constructed on the fly and within a certain context. They're not stored away in a memory and retrieved, manipulated, and so forth. We combine them into different symbol structures, but the fundamental atomic symbols remain the same. This is not the case with an artificial neural network. And of course, when it comes to neural networks, much of the information processing power lies in the way the current state of the network constrains what can happen regarding future states of the network as well. Another reason why we say these are dynamic representations. So that's just a little bit about second generation networks. What about third generation networks? Well, third generation networks place an even more emphasis on temporal dynamic properties. Sometimes we call this dynamical connectionism, kind of taking what Ellman was talking about that I just mentioned a moment ago and kicking it up to the next level. Dynamical connectionism introduces new and even more biologically plausible features into neural networks, like special purpose units. So neurons in the brain are specialized. We have different kinds of neurons in the brain. So why don't we have different kinds of artificial neurons? Well, now we do, to make them more biologically plausible. We have multiple recurrent pathways, so we have much more complex connectivity in third generation neural networks. These would be the kinds of neural networks that are found in this kind of research at the present time, by the way. We also have things like salient time delays, the deliberate use of noise, all to try to make these networks more biologically plausible. And we will encounter these again as we proceed throughout the course. For now, just keep in mind that the first and second generation of artificial neural networks move farther and farther away from the picture of computation we get from the symbolic paradigm. And they do this by incorporating more and more dynamics and more temporal processing. Now, of course, there are even more advanced networks, like, for example, one based on the Helmholtz machine that Clark talks about briefly towards the end of the sketches section of this chapter. The really cool thing about the Helmholtz machine is that it uses probabilistic learning and stuff so that it can engage in unsupervised learning. It doesn't do supervised learning like the networks we talked about today. It can learn in an unsupervised manner, which is pretty cool. But we're not going to talk about this a lot today. We're going to come back to this later in the course. For now, the things that I want you to keep in mind about neural networks are that they have kind of spurred what Clark calls an inner symbol flight. You know, a flight from this classical AI, physical symbol system paradigm picture of cognition as the manipulation of symbols and symbol structures according to rules by these syntactic engines, right? We're moving further away from this idea of the mind as a central processor that manipulates static, discrete, neat inner items according to rules. And we're now much more sensitive to dynamics and to temporal considerations, you know, to what we face in the real world. We have time constraints, and we face a world that is not static. It is dynamic, and it changes constantly. We contend with this, so if we're going to understand minds that can contend with this, we should try to build minds that can contend with this. And that's what we're doing with second and third and subsequent generations of research in connectionism and parallel distributed processing. Of course, all these networks are getting more and more biologically plausible. We saw this earlier. The first generation networks were only roughly analogous to what goes on in the brain. Now we have specialized artificial neurons and recurrent networks, and we're trying to get closer to what's actually going on in the brain biologically, although we're still not there yet. And by the way, I could go on and on about the ways in which we've succeeded and failed at this, but that would take us very far afield and down a neural network rabbit hole that we probably don't want to go down right now. So suffice to say, if you have any questions about anything I've talked about today, just send me a message. Discord, email, YouTube comments. You know how to get a hold of me. Now, Clark sees all of this as a very laudable transition, but it brings up the transition to, away from symbol systems, this inner symbol flight, to dynamic and temporally sensitive neural networks is laudable. It's praiseworthy. It's where we should be going. But it raises a new set of concerns and challenges. And that's what we're going to take up next time when we look at the discussion section of Clark Chapter 4. All right, so that is all I have for you today. I just want to summarize real quick. We've covered section 4.1 of Chapter 4. That's the sketches section. So we've talked about basic concepts that you need to understand what neural networks do. But of course, this survey has not been exhaustive. Clark's survey in this chapter is not exhaustive, and even with my supplements, my survey has not been exhaustive. So this is, this is an area we barely scratched the surface on. But like many of the topics we've already encountered, we will come back to these ideas in the near future. So we've talked about basic concepts. We've talked about how neural networks are often used in machine learning applications for research purposes. We use learning algorithms and we train them rather than programming them. I've tried to fill in some of the details, but there's lots more details out there. So if I've missed anything, please don't be shy to reach out to me. So next time we're going to cover the discussion section. And I should be in the thick of grading your critical responses by then as well. So I hope to have some feedback for you by next week. I'll keep you posted. And if you have any questions once you receive your feedback, of course, don't be afraid to get in touch with me. In the meantime, that is all. I will see you next time for our discussion of the concerns and considerations surrounding what we've talked about today. In the meantime, take care of yourselves and stay safe. Bye for now.